Welcome to Maths with EJD. In this video, I'll be starting with Laplace Transform, which we can see in a way as a continuation of differential equations, though it's a standalone playlist and it is going to contain more things that are probably not related to differential equations. So let's follow along and see how this powerful technique works. So the Laplace transform is a powerful mathematical tool used to convert complex differential equations into simpler algebraic equations. Making them easier to solve. It is widely applied in engineering, physics, and control systems to analyze dynamic systems, circuits, and mechanical vibrations. Okay, now the question, let's look at Laplace transform itself, the definition. So, what is the concept behind and the motivation behind the Laplace transform? Concept and motivation. So, the Laplace transform provides a way to shift from the time domain where functions describe real-world behavior over time to the S domain, to the S domain where problems become algebraic, where problems become algebraic. This transformation simplifies the process of solving differential equations by converting differentiation into multiplication. So a good example Instead of solving y prime prime plus 5y prime plus 6y equals 0 directly, of course, we can solve that using characteristic equation method. So, but here we can actually apply the Laplace transform, the Laplace transform to get an algebraic equation in S, which is easier to manipulate. Hey, so let's look at the definition and basic formula. In essence, the integral definition and notation. Integral definition and notation. Okay, so the Laplace transform of a function in the time domain, that's a function f of t, denoted by L of denoted by L f of t, or big F of s, is defined as big F of s equals the Laplace of f of t, and that is equal to the integral from 0 to infinity of e raised power minus st f of t dt. So you see this t now, for the t, I mean, you have f of t here, and you have e raised power minus e raised power st dt. So whatever f of t is, it takes over in that place, and then you can operate things together and you get your results. So here we have the following, that first of all, s is a complex frequency parameter. Complex frequency parameter. On the other hand, we have e raised power minus st, which acts as a damping factor. It acts as a damping factor, ensuring convergence. In a way, we can call it the kernel of that function, because it's like, it's always there. So whatever comes joins it, so to speak. So let's talk about the existence of Laplace transforms. Existence. Okay, let me go this way. Existence of Laplace transforms. So talking about conditions for convergence. So a function f of t has a Laplace transform if, one, it is piecewise continuous on the semi-closed and open interval 0 to infinity. So 0 is involved, but it doesn't get to positive infinity. So it is piecewise continuous. Then the second thing is that it satisfies the exponential order condition. The exponential order condition. So exponential order condition, that is, there exists, there exists constants, there exists constants big M, small a greater than 0. So we have constant big M, then small a, which is positive, such that the absolute value of f of t is always less than or equal to me raised to power at. That's for large t, for large value of t. So that's the condition there. So, for example, f of t equals e raised to power 2t does not have a Laplace transform, does not have a Laplace transform for all s because it grows too fast. Okay. And because of the fast growth, it doesn't seem to converge at the end of the day. Okay. Then, secondly, we have f of t equals e raised to power minus 2t, which is valid since it decays exponentially. So it decays exponentially. Now, let's move on to another idea where we talk about Laplace transform of elementary functions. Laplace transform of elementary functions. So some very common functions and their Laplace transforms. Okay. So let's start with the first one where we have the constant function. The constant function. And the constant function f of t equals 1. So when the function is constant, whether it's 1 or any other number, as far as it doesn't have a t attached to it, then this is how the Laplace goes. So we have the Laplace transform of 1, we just be equal to integral from 0 to infinity e raised to power minus st dt. Normally, it should be e raised to power minus st times 1. In fact, let me put that there. So this is times 1, okay? And in that case, we just have integral from 0 to infinity e raised to power minus st dt. And if you integrate this, right, just see that the Laplace of 1 is like, when you integrate e raised to power minus st, differentiate e raised to power minus st, you get minus s to divide this expression. So it's like you have e raised to power minus st divided by minus s from 0 to infinity. Okay, so this is so that will be, you can now substitute the let me see. So e raised to power minus st is up there. Okay, and it decays so fast. So at the end of the day, you have e raised to power minus st. If you substitute infinity, okay, it's a function of t actually, so that makes sense. So we can have so you can bring out minus 1 over s. Yeah, I think that makes sense. E raised to minus st from 0 to infinity. So that is minus 1 over s into you can now put infinity. You have e raised to minus s infinity minus e raised to minus s 0. So when you substitute the interval, so that's minus 1 over s into e raised to minus infinity minus e raised to minus 0. Okay, like that. So that is minus 1 over s, okay, into e raised to minus infinity is simply, it's more like 1 over e raised to infinity minus 1 over e raised to 0. Okay, so this is minus 1 over s into 1 over infinity. This is like 1 over infinity minus 1 over 1. Okay, so this is minus 1 over s into 1 over infinity is 0 minus 1 over 1 is 1. So you have minus 1 over s into minus 1. So you have 1 over s. So in short, we are saying that we can say, therefore, the Laplace of constant 1 or any constant number for that matter will just be that number multiplied by 1 over s. So we just have 1 all over s. So that is the Laplace of a constant like that. So that goes. Then number 2, we can talk about an exponential function. Exponential function. So we have f of t equals e raised to power at. Okay, so we are saying now that Laplace of e raised to power at is the same thing as integral from 0 to infinity of e raised to power minus st, then e raised to power at dt. All right, and with that now we have integral from 0 to infinity of e raised to power e raised to power e raised to power minus st plus at dt. Okay, that's integral from 0 to infinity of, we can, t is common, so we can have e raised to power minus s minus a t dt. Okay, because if you open this up, you have minus s plus a. So, and from the experience we had up here, right? Whenever you have e raised to power minus s like this, so that's going to give you, um, okay, I mean, let's just do it. So if you integrate this, if you integrate this now, you're just going to have e raised to power minus s minus a t divided by, when you differentiate this part, you get minus s minus a. So this minus s minus a goes to divide down here, and the whole thing is from 0 to infinity. So you can remove the constant part, which is minus 1 over s minus a, and that's into e raised to power minus s minus a t, from 0 to infinity. From what you have done before, right, you can already see that this is minus 1 over s minus a into, if you put infinity here, so if you put infinity, you have e raised power minus infinity, and if you put 0, you have e raised power minus 0. And just like we saw before, uh, this is 1 over minus 1 over s minus a into e raised power minus infinity is 1 over e raised power infinity, which is 1 over infinity, and that will be 0 at the end of the day, minus e raised power minus 0 is 1 over e raised power 0. That's 1 over 1, and that is 1. So at the end of the day, you just have this to be 1 over s minus a. So in short, we are saying that the Laplace transform of e raised power at will just be 1 all over s minus a. Okay, when it was, okay, yeah, 1 over s minus a, and that is just what that gives you. Okay, we can go for the third one. How do we find the Laplace of f of t, which is sine bt? By the way, here, it's important to know that s must be greater than 0. S must be greater than a, rather. S must be greater than a. Very important. So for the first one we did, right? Here, s has to be greater than 0. S here has to be greater than 0. Very important. Then what else? Yeah, we go for the third one, which is sine function. So how do you find the Laplace of a sine function? Okay, so that sine function, the first one we did was constant function, f of t equals 1. How about sine function now, which is f of t equals sine bt. How do we find the Laplace transform of this? So of course that will be Laplace of sine bt equals integral from 0 to infinity e raised power minus st sine bt dt. Okay. Um, so one way to do this is we can actually make that into and into exponential form, if you remember, under complex numbers. So we can do sine and cosine together. Um, so here you can let you know that recall, right? Recall that e raised to power I um is it it e raised to power it, right? Should be I cos theta, I cos t. Let me see. So I think that should be e raised to power. Is it theta I now? I'm trying to remember this. Mm, okay, let me see. Let me see. I think it's the Euler formula or something like that. Yeah. Okay, good. E raised to power ix is equal to cos x plus I sine x. So let me see. Let me see this. E raised to power I bx now, or I bt. So, because of that bt, right, we can simply say that e raised to power I bt is the same thing as cos bt plus I sine bt. Okay, so you can recall this. So if we do this, in fact, we can do sine and cosine together. In fact, let me put the two together. Sine and cosine functions, where for this f of t is also equal to cos bt. So by approaching it this way, we can do both at the same time. Okay, so we know L sine bt is this, and the Laplace again of cos bt will just be integral from 0 to infinity of e raised to power minus st cos bt dt. Okay, but recall this, right? If you recall this, we have that the integral, we have that the Laplace of e raised to power ibt will just be integral from 0 to infinity e raised to power minus st times e raised to power ibt, all right, e raised to power ibt dt. Okay, so with this now, it makes things a bit easier. So we have integral from 0 to infinity e raised to power minus st plus ibt, okay, dt. So this is integral from 0 to infinity e raised to power minus s minus ib t, like this, dt. And just like we know, so this will be integral. So if we integrate this, right, we just have e raised to power minus s minus ib t all over minus s minus ib, okay, from 0 to infinity. So we move on to say this is minus 1 over s minus ib, okay, then into e raised to power minus s minus ib, s minus ib of t, 0 to infinity. Is this going to work? Is this going to work? Um, First of all, is integration okay? I think it is. So if we could just put this now, we have as usual 0 minus 1. Okay, yeah, we have 0 minus 1. Let's just go. So we have, as usual, this is minus 1 over s minus ib into minus 1, as we know already. Because if you put infinity for this, e raised to minus infinity, that would just be minus 1. So this is just 1 over s minus ib. So far, we have the Laplace the Laplace transform of e raised by ibt is equal to this. So with this now, we can actually, we can, what is this called now? We can take there's a word for it. Um, when we multiply by the conjugate, when we multiply by the conjugate, I think it's, I've forgotten the word, okay? We also use it for sod, okay? So we have 1 over s minus ib. So, and we multiply by its conjugate. So that's s plus ib all over s plus ib. That's, it's not natural. No, it's, I've forgotten the word. Maybe I'll remember before I finish. So this is now, s plus ib all over s minus ib into s plus ib. So we can see difference of two squares playing out there. So we have s plus ib all over all over difference of two squares, s squared minus ib all squared. Okay, so this is s plus ib all over s squared minus I squared b squared. Interestingly, uh I right, I is equal to -1. So I squared, I is square root of -1. So I squared is square root of -1 times -1. So I squared is equal, it will simply be um I guess I'm taking it too far. Okay. I is square root of -1. So I squared is square root of -1 all squared. So I squared is simply equal to -1 like this. Okay. So we can go back here and have the Laplace of e raised by ibt is equal to s plus ib all over s. This is minus, so we have -1 b squared. Okay. So that is s plus ib all over s plus b squared. So we can split this up. We have L e raised by ibt is equal to, we can split it into two parts. So we have s all over s plus b squared, and we have plus I b, this is s squared, I b s squared plus b squared. And we know that the part with I is the cosine part, right? Okay, so we know generally this this goes with the let me see again. That thing can be a bit tricky. Okay, yeah. The I goes with sine, okay? So this goes with cosine. The one without the I goes with the cosine, and this part goes with the sine, okay? So what do we conclude? We can just simply now say that we can then go ahead and say that L, the Laplace of sine bt, which is the same thing as integral from 0 to infinity of e raised by minus st sine bt dt, is simply, for the sine part now, we have b all over s squared plus b squared, where s must be greater than 0. Okay, so in short, we are saying that L sine of bt, okay, is the same thing as b all over s squared plus b squared as derived up there. We have that. Then we also have, for cosine, the Laplace transform of cos bt, okay, which is the same thing as integral from 0 to infinity of e raised by minus st cos bt dt is equal to that cosine part, which is s all over s squared plus b squared. So s all over s squared plus b squared, where s must be greater than 0. Okay, so in short, we are saying that the Laplace transform of cos bt, okay, is equal to s all over s squared plus b squared. So from what we have derived, so that goes. So you can have all that. So these are basic transforms this, okay, in conclusion, right, we can conclude now. So conclusion, so basic transforms, these basic transforms form the foundation, they form the foundation for solving complex differential equations, for solving complex differential equations efficiently. Okay, so that's quite a journey. So that works. All right, so we are done with this first part of this video. You want to go through it to be sure you really grasp it. But so we are going to be, so this is the foundation for all the things to be doing after now. So let's see how we move on. In the next video, I'll be talking about the properties of the Laplace transform. So so understanding those properties will make us do it to even work more smartly, like to be smarter in using Laplace transform. So go ahead and tell me in the comment section how helpful this video is for you. And if you want me to teach a topic or solve a problem, and of course, if you have not subscribed to this channel, you'll be missing out a lot. So be sure to subscribe right now. And for those who have subscribed, thanks a lot. And everybody, please don't forget to hit the notification bell so you can always get alerted each time a new video is released. Then be sure to like and share also so that more people can have access to the great content we have right here. Till I come your way again, keep doing maths right. Watch out for the next video where I talk about properties of Laplace transform. Bye.